Now, before we go in detail of second law of thermodynamics, first try to understand the meaning of thermal energy reservoir. So it is sufficiently large system in stable equilibrium that can supply or absorb specific amount of heat without any change in its temperature. For example, if it is the case of atmospheric air, and if you absorb the heat from the atmospheric air or if you give the heat to the atmospheric air, then it is such a large reservoir that there will not be any much substantial change in its temperature. So let us take into consideration the meaning of heat source and heat sink. For example, heat source means what? It is a thermal reservoir which is at a higher temperature and it supplies the heat. For example, boiler furnace, combustion chamber, from which the heat is supplied. If it is a boiler furnace then and a combustion chamber together, then we are having the water which is receiving the heat from the combustion chamber. Grate of On the grate of the combustion chamber, the fuel is placed, and when the burning of the fuel takes place, then that heat is supplied to the water which is present inside the boiler, and then the steam is raised. Similar to that, if you are having the another definition, that is heat sink. So it is a thermal reservoir which is at a lower temperature and receives the heat. For example, just now we have seen that atmospheric air. So the high pressure, high temperature gases, they expand on the piston of the IC engine, and then exhaust gases, they will leave to the they will be given through the silencer to the surrounding, that is the atmosphere, and there will not be any much change in the temperature of the atmosphere because of those particular gases. So atmosphere or atmospheric air is the heat sinks where we are rejecting the heat, and heat source is the place where we supply the heat to the any particular system. Now in case of the heat engine, which is the application of the second law of thermodynamics, we supply the heat by burning the fuel at temperature T1, and heat is rejected to the sink at temperature T2, and by supplying heat, certain portion of the heat is converted to the work. So here we can say that this is our thermodynamic system. Engine is the thermodynamic system where there are conversion of energy or transfer of energy. So heat energy is converted into work energy. So this is the thermodynamic system. Suppose Q1 is the heat supplied, W is the work produced, and Q2 is the heat rejected. Then applying the energy balance to this system, thermodynamic system, arrows entering into the system and arrows going out from the system. So we can say that Q1 is the heat supplied to the system, and these are the arrows W, and Q2 are the outgoing arrows W plus Q2. So we can say that W is equal to Q1 minus Q2. So work done is equal to heat supplied minus heat rejected. Now efficiency is output upon input. So this is the output and this is the input. So output is nothing but W, that is work that is produced, and heat supplied is the input to the system, thermodynamic system. Similar to that, we are having the another application that is known as the refrigerator. But here we are supplying the work to the thermodynamic system, and as the work is supplied to the system, we can say that it is a negative type of the work. And in the previous case, this rotation was clockwise. Now it is the anti-clockwise rotation. Whenever there is a power absorbing device, we are having the anti-clockwise rotation of the cycle, and whenever there is a power producing device, then it is a clockwise rotation of the cycle. So work is required to abstract the heat from the lower temperature and transfer it to the higher temperature. So heat is abstracted from the space to be conditioned, or from the space whose temperature is to be reduced, and then that is known as the refrigerating effect produced. That is possible only when we are supplying the work to this particular system, and then the heat is abstracted from the lower space and it is transferred to the high temperature source. So from the sink, the heat is abstracted, that is known as the refrigerating effect produced with the help of this work input, and then the heat is given to the high temperature source. Here source is nothing but the atmosphere, surrounding atmosphere. Here also, if you apply the heat balance, then Q1 will be equal to W plus Q2. That is, these are the two incoming arrows to the system, where this is only the one outgoing arrow from the system. So Q1 is equal to W plus Q2, or you can say that W is equal to Q1 minus Q2. So heat rejected minus heat abstracted. The performance of this refrigerator is given by coefficient of performance, that is output divided by input. So output is nothing but the cooling effect that is produced, or a refrigerating effect that is produced, or heat that is abstracted from the system, to the input, that is work given to the system. Another application is that of the heat pump, where the energy balance equation, as we have just now seen, will be same. Here also the heat is rejected to the source, which is at a higher temperature. Whatever the heat that is absorbed because of the application of the work from the low temperature sink is given to the high temperature source. In the previous case, in case of refrigerator, the purpose of the refrigerator is to maintain the temperature of the sink below the atmosphere. Here, the purpose of the heat pump is to increase the temperature of the source much higher than the temperature T1. So purposes are different for heat pump and refrigerator. Otherwise, energy balance equation is same. That is, incoming arrows are W and Q2. So W plus Q2, and outgoing arrow is Q1. So Q1 is equal to W plus Q2. W is equal to Q1 minus Q2. But here the output is nothing but what? How much amount of the heat that is rejected to the source, so that when the source gets this amount of the heat, then its temperature is increased. So purpose is to increase this temperature T1. For example, if previously it is 1000 Kelvin, then purpose is to increase it to 1200 Kelvin, like that. So coefficient of performance or energy performance ratio is output divided by input. So here output is Q1 and input is work required. So these are the applications of second law of thermodynamics. Now if you consider the coefficient of performance of the refrigerator, it is Q2 upon W. Adding 1 on both the sides, so 1 plus coefficient of performance of refrigerator is equal to 1 plus Q2 upon W. Cross multiply by this W to this 1, so it is W into 1, that is W plus Q2 upon W. So W plus Q2 is nothing but it is Q1 from the energy balance, so it is Q1 upon W. So this Q1 upon W is nothing but what? It is the coefficient of performance of the pump, heat pump. So we can say that coefficient of performance of the heat pump for the same temperature limits, it is 1 plus coefficient of performance of the refrigerator.